All right, so welcome back. This is the second half of our fourth lecture. And in this portion of lecture, we're going to revisit the single neuron model with respect to something called linear regression. Now, in the previous lecture, we learned about using a linear model to classify two species of the flowers from the iris dataset, right? So this linear model has shown promise so far with regards to classification, and now we're going to show that it also has promise when considering regression. Okay, so before we get started, we should probably recall that script X is the space of all measurements, and script Y is the space of all corresponding labels for those measurements. And that there is some optimal target function f that assigns each measurement the correct label in Y. And moreover, in supervised learning, we have access to some of these pairs of data. We have access to some subset of the measurements and their corresponding labels, which were generated by the target function f. Now, unlike classification, which we covered in the previous lecture, in regression, we're given labeled data where the labels are real values. Okay, so this supervised learning task is about predicting real valued target labels. And again, these target labels are generated by this unknown target function f. Okay, and here's a little diagram illustrating the differences. Last time we performed classification, which is basically finding a separating hyperplane. Now we want to find a function that approximates the data in this case, linear way. So we're focusing on linear regression, and this specific case of regression assumes that the target values y are approximated by some linear function. That is, the optimal target function can be assumed to be roughly some linear function. Now, this picture above, this is not a linear function, but we could maybe approximate that same type of data here with a linear function. And many types of problems and data fall into this category. And one such example we can take from this this toy data set, or not, well, maybe I shouldn't call it a toy data set, but this iris data set. And specifically, if we consider as input the sepal length from the Setosha species of flower as our input, and the targets would be possibly, or in our case, the sepal width of the Setosha flowers again. Now, we can kind of visualize this possible linear relationship by running the following code. And as always, I have these three packages that I'm going to import: matplotlib, numpy, and pandas. And then because I like the Seaborn theme, I also import Seaborn. I'm going to read in my data set from the directory datasets, and then there's my iris data set that I have saved. Hopefully all of you know what I mean by now with that. And then this pandas read CSV converts that data into a pandas data frame. But I only want to look at the Setosha species, which are the first 50 entries, so 0 through 49. And I want to only focus on the sepal length and sepal width for teaching purposes in this lecture. All right, so then I set my figure size, and then I scatter the sepal length versus the sepal width, give it my favorite color, or my second favorite color, light sea green, give it a label, and then as always, all of you should label your axes. I give my axes label, set the font size, plot my legend, and then give a title. So let's just run this code here and see what happens. All right, so here is my data. And just visualizing it, we can see that there could be a way of approximating the sepal width as a function of the sepal length, right? If there is a line that we can find that kind of cuts through all of this data, if we can find such a line, then we would have a rough approximation of the sepal width of these setosa flowers based off of sepal length measurements. So again, we're trying to approximate a target function that is more or less hitting all of this data in a linear way, for linear regression, that is. So before moving forward with this idea, we need to recall our general machine learning framework or model that I kind of took from several different people's lectures in the past and made my own. And I think that this is kind of an appropriate model. We have an unknown target function that maps features to labels, in our case, real valued labels. There's training and testing examples that were given by this target function. We're ignoring the testing right now, but we will get to that very soon in another lecture. For now, we're just going to try to understand the model itself. But given this data, we have a learning algorithm or model and learning algorithm that searches through a hypothesis set for an appropriate hypothesis to the target function on the data that we're observing. Now, because our target function is assumed to be linear function of the input features, and because we have experienced in the last lecture that single neuron models are good at function approximations, we will next build a single neuron model and change our activation function to be linear. Now, if you recall lecture 3, the choice of activation function is determining, it determines what your model is going to do with relation to the task at hand. The activation function is the most important thing for deciding whether or not you're doing classification, like the perceptron, or regression in our case. So we have to choose a specific activation function for our model that will be beneficial for the regression task at hand. So we're going to choose a linear activation function. Okay, so we're trying to predict a linear function. Our activation function should be linear. Furthermore, we're going to use a new cost function for our model, which again, all single neuron models have a cost function. And this cost function is called the mean squared error cost function. So basically, we have a cost function of our weights and biases, and we divide the sum by 1/2 times n, where n is the number of samples in question. And the sum is taken over our predictions minus the actual label in question, and then we square it. Now, with regards to optimization and something like gradient descent, notice that this is a quadratic function, right? This is some type of bowl-like thing, and there's a hope that if we apply something like gradient descent, there's a hope we might find the global minimum of this function of w and b. And again, w could be a vector or it could be a single like scalar value. All right? But so for teaching purposes and really just trying to understand the fundamentals, we're gonna suppose that w is just a single variable, meaning that we're looking at this image here, where we have a sepal length, we multiply a given sepal length by a weight, we add a bias, and then that's going to produce our input to our single neurons, or our pre-activation value, which I denoted by Z last time. So with this specific case on the iris data set, we have a feature measurement, which is sepal length, that we pass into this input neuron. We have our bias input neuron, which we always pass in 1. So there's a weight 1 on this edge here, B on this edge here. We take the weighted sum of this input and the bias. That's our pre-activation value. And then our post-activation value is, it depends on the activation function. However, for linear regression, we're going to choose this very simple linear activation function where we just return Z. So in our case here, A is really equal to Z, and A is what's passed to Y hat. So our prediction will be literally the weighted sum of the input feature and the bias. And our cost function is this mean squared error. So if we can minimize this mean squared error, that means that more or less our predicted y hats are hitting the actual target values generated by the target function f, right? So the smaller this cost function is, the better our model is at approximating the data. So we need to minimize this cost function. So we're going to end up making a class to kind of encapsulate all of this data and these functions into attributes and methods. But before we do that, we need to kind of discuss for a moment how to minimize this specific cost function, right? And this cost function, this W right here is really just W1, and then we only have one B always here and for single neuron models. So our goal will be to find, to solve this problem, min over W1 and B of the cost function C with inputs W1 and B. Now, this function C is a differentiable function of both W1 and B because our activation function that we chose is Z, which is just this linear combination. So the output passed into the cost function, this y hat, everything here is differentiable. And when we have a differentiable output with respect to W1 and B, we can apply the gradient descent algorithm, which would be W1 is equal to W1 minus learning rate times the partial of the cost function at W1, and the same for the bias. Okay. Now, how do we compute these values? So the reason why I mentioned that is when I first encountered these types of machine learning tasks, I was kind of confused as to how the cost function is only a function of W1 and B because there is a relationship to the data that you're using, right? Like you pass in your data and you get an output. How is the cost function not a function of the data? Well, it's because the data that you're using when training doesn't change, right? That's kind of a set in stone thing. You can think of the data that you're using literally as just like coefficients, if you will. Like they are just coefficients, and the true variables of your cost function are not the X and Y, but the W and B. With that being said, we should probably try to understand how to calculate these derivatives with respect to the data that we're training on. And I found the best way to do this is by considering a single example of training data. And that's what we're going to start off with. So if we have a single example of training data, i.e. capital N is equal to 1, then this cost function reduces to this right here. And I use a semicolon here to indicate that we're with respect to a single entry xi and yi. It's this very simple function. Now, recall that in this model, we've chosen a linear activation function, a very simple linear activation function, right? Which means that y hat is just equal to a, which that's always the case. But because of the function we chose, a is just equal to z. And z is equal to this linear combination. The weight times the x input plus the bias. Thus, we may rewrite the cost function with respect to our single observation of data as follows. All it is 1/2 times that linear combination, like this is y hat, minus y, which is the true label, all squared. Very simple function. Once we have this function, it's very easy to calculate the partial derivative of this function with respect to W and B, right? We just apply the chain rule. And again, if you have this notebook, you can just click on this link and there'll be a nice little refresher on YouTube for like reminding you how to work with the chain rule. Now, if we apply the chain rule to this and we take the partial derivative with respect to W1 and to B, we get these equations. And hopefully that's really easy to see. So for example, if we were to take the partial derivative of the cost function with respect to W1, we apply the chain rule. So it's 2 times a half. So the half goes away. We're left with the inside times the derivative of the inside with respect to W1. The derivative on the inside with respect to W1 is just X. So when we find the partial derivative with respect to W1, we get precisely this term right here. The differences in between the Y's, the predicted Y and the true Y, times the X value. Again, to emphasize this one more time, you can think of the training data as set in stone, and those are basically the coefficients of the variables W and B. Now, if you understand that, hopefully you'll understand how to find the partial derivative of C with respect to the bias term. So when we take the partial derivative of this function with respect to B, again, chain rule says 2 times a half, the half goes away. So we're left with the inside times the derivative of the inside with respect to B. What's the coefficient of the bias? The coefficient of the bias is just 1, right? That's the only thing multiplying B. So when we take the chain rule, or when we apply the chain rule, there's only a 1 multiplying the differences between the predicted Y and the true Y. So then we observe that the partial derivative of C with respect to B is just the differences in Y. Now, this is essential in understanding how to calculate these partial derivatives is essential in optimizing our cost function, right? And luckily, gradient descent is a first order method. So if we can just find those first derivatives, we're good to go, and we can try to apply the gradient descent method. Again, I hope that in the previous notebook, lecture 4.1, you click on the link to the Nocedal and Wright textbook, and you kind of take a look through it, just to get a broader sense of how, how awesome they write on optimization. Honestly, it's a great book. Okay, so now that we know how to find these partials, we should discuss how we can possibly implement the gradient descent algorithm based off of the fact that we're using this over a collection of data, and that collection is kind of determining the look and feel of the derivatives of the cost function and the partial derivatives of the cost function. So because we're able to calculate it at a single example, it's not hard to kind of extrapolate this to the full partial derivatives with respect to every sample. More specifically, all we have to do is sum up those examples, and those partials. So if we want to calculate the full gradient or the full partial derivatives, all we have to do is to sum every single one of these partials over each sample. And that's what's shown here with these equations. All right. Now, calculating this full gradient with respect to all training data and then applying the gradient descent algorithm is called batch gradient descent. And it's the most similar to what we did in lecture 4.1 with optimizing those functions in that lecture. So how does it work? Well, for each epoch, remember that an epoch is basically considering each training example. So for each epoch, we're just looking at all of them in this case. We calculate the full gradient by finding the full partials, and then we update our weights and our bias using those full partial derivatives. Now, applying this method will work. So applying batch gradient descent is a way to minimize the cost function. However, this method can be very slow and use a lot of memory, especially when the number of training instances is very large, possibly millions. Right? Like, for example, think about a neural network that is associated with like a self-driving car. Like, how many images are in the training examples for a network or neuron learning on that data so that they're not going to crash into a wall or something? It's millions of data that these things have to learn from. So storing and calculating the full derivatives, full gradients for that type of data is not, it's not going to work. But more importantly, batch gradient descent is not necessary to find these local minimum of the cost function. And the way to fix this is what's called stochastic gradient descent. That stochastic gradient descent is very similar, if you think about it, to what we did with the perceptron update rule. We encountered each, like one at a time, we look through the data, and then we update the weights and bias. Same thing here. For each data, so for each epoch, and then for each data point, we calculate the partials with respect to that single data point. And then we update the weight and bias each time without having to store all of that, all those numerical values over and over and over again, and having to calculate that stuff over and over and over again. So essentially, it's this right here. For each data point, we calculate this value here and this value here, and then multiply that times the learning rate and subtract that off of the previous weight and bias respectively. And that's what we're going to do. And we're going to do that in a very professional way with a Python class object called a single neuron. Notice that I included a doc string listing the attributes and the methods. Again, attributes are data contained in the class instance, and methods are functions specific to that class. I have a big list here describing to the reader what the things do. Now, I probably need to update this to show how to instantiate such an object. The only thing that I'm required here with this double underscore init method to instantiate a single neuron class is a function. And again, single neurons behave according to the function, the activation function that you pass to them. Like for example, this single neuron called the perceptron has an activation function sign, and it's going to do a classification task. In our regression model, we have a linear activation function. So I'm doing this to set the stage for a general framework where we have a given class that we write, and then depending on the task at hand, we choose from some collection of activation functions, just throw that into the class and use this object over and over again whenever we want. Moreover, I would like to call your attention one more time to the perceptron, and that the update rule for the weights and bias, it's the same thing. And that's why I wrote the perceptron the way I did. Look at the weight update. Weight minus a numerical value times the difference in y times x, and then bias minus some numerical value times the difference in y. It's the exact same thing. In fact, the perceptron update rule is a discrete approximation for the gradient descent algorithm. Recall that the sign function is not differentiable, right? It's not differentiable at 0, for example. But still, the update rule that was designed before any notion of gradient descent was available to these researchers, that update rule is a discrete approximation to gradient descent. And it looks exactly the same as gradient descent for this linear regression. The weights, learning rate times difference in y's times x, bias minus equals learning rate times difference in y's, same type of thing. The only difference is that the cost function is a little bit different, but only different by a factor of 1/2. So this single neuron class we're making should also work for the perceptron, not only linear regression. All right, and we'll elaborate on this more when we get to logistic regression next week. So I'm going to go ahead and copy this. We have a predict method, which just returns pre-activation passed into the activation function. We have gradient descent inside of the train method. Let's go ahead and run this and see what happens. Well, we're not running anything, we just defined it. But now that we've defined our single neuron with activation function, when we call the train method, we set our weights, keeping track of our errors, number of samples, update our, it should be clear what's going on here. Now, before we do anything else, we need to format our data into a way that we can feed it in to train our single neuron. So what I'm going to do with this code here is convert my sepal length values into a NumPy array. Now, this is something that I can't emphasize enough, this caution. When I do this, so x is equal to df.sepal length dot values, and I check the shape of this thing, notice that there's not a 1 in the column space. This is because when you convert this, this column of data into an ND array, it does not by default set it equal to a good representation of a column vector. And when you're dealing with NumPy and multiplying vectors and matrices and these types of things, it needs to be in a column vector form if it's being used that way. So this reshape method needs to be called not only with my class that I wrote right here, but with scikit-learn, TensorFlow, PyTorch. Anytime you have a feature vector with only one measurement per entry, you have to convert it using the reshape method with a -1 and 1 so that it becomes a column vector representation. So notice, like, just again, just to emphasize this caution, I set x equal to that, and then I do this reshape. So prior, the shape was 50, nothing. After, if I make it equal to the reshaped vector or ND array, there's a 1. Now it's an appropriate representation of a column vector, and that's the way that you will have to do it whenever you have feature vectors with a single measurement only. If your feature vectors have 2 or more measurements per entry, you don't have to worry about it. But single measurement ones, you always have to do this regardless of the library you're using. And with my class, that's the way it's going to go. My single neuron class that I've defined. All right, so let me just finish off this preprocessing by making y equal to df.sepal width dot values. So now we have x measurements and then y measurements. And we can verify that we have the correct measurements by running this code. We're just going to plot it. We've verified that we've formatted things correctly. If we plot it and it looks the same, we should be good to go. There's our data. All right, so now that we have our x and y data, we can train. But first, we need to instantiate an instance of the single neuron class. And to do that, we need to pass in a function. And we're choosing the linear activation function. So I define the linear activation function, and then I instantiate the single neuron class with that function and assign that to the variable node. Next up, I call the train method on my class. I pass in x, y, which have been formatted correctly. Again, x has been reshaped to be a column vector. That's what we need to do. And for teaching purposes, I chose a very small learning rate and a very small number of epochs, again, for teaching purposes. And you'll see why in a moment. So if I run this code, I've trained it. All right. So I've called the train method. It's been trained with that learning rate and that number of epochs. So we can visualize its predictions by calling the predict method that we wrote in the definition of the class. So what we do is we define a domain to plot that prediction over. So it's like the minimum value of x minus 0.5, maximum value of x plus 0.5, and I make 100 points in between them. Set my figure size, scatter my data, and then here I plot my domain, which I defined in there, and then node.predict, again, to reemphasize it, that domain I have to reshape to be a column vector. I have to do that when there's only one measurement. So this is an ND array with like one measurement in a sense, and that's what I'm going to pass into my predict method, which is the function that's going to use the weight and bias that were learned during training to predict out a Y value. Label my axes, give a title, put a legend, and let's see what it looks like. Not bad. That's definitely not random. Even with that small learning rate and that number of epochs, that's not a randomly produced line, right? Like when we created our single neuron class here, we initialized the weights to be random. And this line that it just produced does not look random at all. And we can verify this by looking at our custom class, our custom single neuron class errors attribute. Again, attributes are data containers basically for classes. And this errors attribute is a list where each entry of that list is the mean squared error incurred after each epoch. So if we want to look at how our mean squared error is changing after each epoch, we can plot the errors. And the way that we do that is by plotting a range of values between the length of the number of things in there plus 1, and plot those other values, the actual like mean squared errors. I give the markers to indicate each epoch, give it a label. Let's see if we were indeed actually learning anything during training. Oh yeah, definitely. Our mean squared error was way up here, and then after 5 epochs, it was already down to 0.10. So we're learning. This verifies to me that things are working, which is sometimes can be deceiving if you look at like the plot generated by predict. Looking at how the mean squared error change or the cost function changes over each epoch, if that thing's going down, you're on the right track. So now that we are confident that it's working, I'm going to instantiate another single neuron, and then I'm going to train it with the same learning rate, but now I'm going to iterate 50 epochs instead of just 5. And then for like visualization purposes, instead of plotting a single figure, I'm going to again call this subplots method from matplotlib. This will be a 1 row, 2 column figure. The total fig size will be 15 by 10. This references the figure, and there'll be 2 axes. Ax 1 is the first column figure, Ax 2 is the second column figure. So then on Ax 1, I'm going to scatter the data. On Ax 1, I'm going to plot the predictions, do the labeling. And then on Ax 2, I'm going to plot the mean squared error. And that's all that's happening here using the matplotlib subplots method. So if I copy that here, paste it, let's see what happens. Beautiful. That's awesome, right? Like now look at our prediction line, our linear prediction line. It's splitting that data in half, and you can see the mean squared error over time. Like by epoch looks like 20, 31, it's still going down, but not very much. It looks like it's definitely learned. And this I think really illustrates what machine learning is. It's this process of a algorithm updating itself over and over again and getting better at it each time. And the way that that's done is by optimizing your cost function of the model with respect to weights and bias, at least with respect to the single neuron model and multi-layer neuron models called neural networks. That's the learning part. We couldn't program these W's and B's by hand to do this. It had to implement a strategy on its own, which the strategy it had at hand was stochastic gradient descent with a given hyperparameter of this learning rate is what you're going to work with. And then with that learning rate, this is what it did. Now, on that note, we should probably look at what happens for different choices of learning rate, right? This is more experimentation to see what happens with these single neurons on this linear regression task. So the choices of alpha, again, will be like before, 0.1, 0.5, oh no, 0.01, 0.05, 0.07, and 0.09, just to see the differences between them. I make a domain to plot over, and then again, I call my subplots method from matplotlib, and now this will be a 2 by 2 grid of figures. The total figure size of the larger grid will be 10 by 10, and then I'm going to loop over each axis and axes, and I can do that with this .flat attribute, and each learning rate inside of alphas. So basically what this is doing is pairing a learning rate with one of the axes, pairing the next one with the next axis, pairing the next learning rate next axis, pairing the last learning rate with the last axes. Okay, so that's what this for loop is doing. And then inside that for loop, I instantiate my single neuron object as node, and then I train the node with that given learning rate, right? So the learning rate is taken from this list, and then I plot domain and then predict over that domain after it's been trained. Then I scatter my data, and then I set a title showing what learning rate was used for that figure that you're about to see. So copy that, paste, and let's see what happens. All right, this is a good illustration here. And so here we have, this line looks okay, this line looks okay. Let me change the number of epochs. I'm just gonna make it ridiculous for a moment and just set it equal to like 1,000. Really see where these things end up. All right, so it looks like a learning rate of 0.01 might be the best out of each of these. And this is after 1,000 epochs for each train method called, which again implements stochastic gradient descent. So it looks like the best one was 0.01. And then notice that, look at 0.07, 0.09, that's where this error came from right here. There was like some floating point precision error that caused it just vanished. Okay, and this is actually related to something with neural networks called the vanishing gradient problem, where the numerical values for your weights and biases are becoming so small that they essentially are like gone with respect to like machine precision. So this learning rate was terrible. It didn't do anything. And again, this is a good illustration of choosing your learning rates. So next up, I want to try maybe smaller ones. I'm going to put zeros in front of all of these numbers here, like that, and then see what happens. Yeah, those learning rates right there were great. Perfect. They all hit it. But just changing that one entry really threw everything off. And this is a really important thing to demonstrate for you guys so that you know that this could be a problem. Now, how would you know that there was a problem like with the learning rate and not with the algorithm that you're trying to implement? Well, the best way is to keep track of your cost function. In this case, the mean squared error. If that thing is going down, you're doing it right. If it's blowing up and it's not decreasing even a little bit, then you probably have something off with your learning rate, and that's what you need to kind of adjust for. All right, so I think this will conclude the recording for lecture 4.2 on implementing a single neuron linear regression model. So I'm going to stop the recording now.